So there's a new project from IBM called TJ Bot that takes a that targets a Raspberry Pi robot and the back end hooks to Watson. Oh yeah.
Wait, the charging port is the same. The probably means the motherboard is the same. You know?
Well, good morning, folks. How was break? Relaxing? Spend it all in airport someplace? I did. So, any questions on Lab 4, which is demoed this Thursday? The pattern is here, after you simulate, and I think you've all simulated one solver, after that, at least one person on the team should be working at hooking that solver to a bus master and getting an image on the screen. That being the first thing to do. Then worry about how you're going to parallelize. Anybody got an image up on the screen yet from the solver? Oh, cool. Okay. How fast was it with one solver? $800 milliseconds with one hardware solver. Okay, that's about right. Did you try more than one? Did it speed up? Was it sublinear?
So we tried one and then we just tried one and then we got a 10x.
You got a 10x speed up with how many of them? So you got about so the slope is about 0.5. The speed up over the number of processes is about 0.5. And that sounds reasonable. 10x speed up, so it got down to 80 milliseconds. Cool. And then you clocked it up to what?
Oh yeah, we pipelined and clocked it up to around 100 megahertz.
And it was yet faster?
Yeah.
Nice. Did you try clocking it above 100?
And then it breaks.
And it probably breaks for a couple of reasons above 100. One is that the QSys bus is running at 100 megahertz. So you can imagine if you're giving sub-cycle requests to the QSys bus, that might be a problem. Did you put a clock bridge on the bus master?
No, so our project plan doesn't use the QSys at all.
Oh, so you went directly, you built your own VGA controller.
Yeah.
Aha. Okay. So you're not limited by bus rates at all.
Not yet.
Not yet. And how are you arbitrating between writers? So there's a scheme that uses, you have a solver which goes to an M10K block, 10K block, 10K block, each one of which, each solver has its own M10K block. And then the VGA controller at plotting time multiplexes between the different blocks to print the screen. So there's never a serial bottleneck. Because, well, there is a serial bottleneck, but it's dependent upon the VGA refresh time, which you can't change. Okay. But this means that the VGA controller has to be custom written and not the QSys distribution.
Yeah, we just used the one that was by Skyler.
And that worked without mod?
Yeah, that worked.
I think one signal name has to be changed or something on that one. Okay, cool. Anybody else got working through the QSys bus? Or any other way? So, you probably got the Piazza announcement today that I want everybody on Friday to do a 2-minute, each group, to do a 2-minute presentation of their final project. And from which you can infer that attendance is required on Friday. So, in case that wasn't obvious. And 2 minutes, how many words per minute can you speak? 1 word a second? 2 words a second. Just close. So it needs to be about 200, 250 words. That sounds like 1 paragraph. You need to write it out and practice it. This isn't something you're going to pull out of your nose while you're up here standing here, right? You're going to come up here and talk for 2 minutes. We're going to ask you questions. No slides, no graphics, 1 paragraph. Any questions on that?
What should be covered in that then?
Well, it should be what you're going to build, why you're going to build it, and maybe how it uses the FPGA resources well. So I would say that projects that use only the HPS side of things are going to require a significant justification about why this is a good idea. Projects that use only the FPGA side, okay. I think that many projects, if not most, are going to use both. For instance, let's say you wanted communication from the PC to the FPGA fabric. It would make a lot of sense to use HPS to do the Ethernet, because otherwise you'll cry. It's really hard to do Ethernet by hand. Although I have seen people roll their own UDP stack in hardware. But you don't want to. So I would guess that many of the projects are going to be using some combination, and that's really what I would prefer, but I'm not going to enforce that. If you want to do all FPGA hardware only, that's okay. Anything else on that? Also, it should be a project which is computationally, in some sense, computationally beyond the reach of a microcontroller. So it could be beyond the reach of a microcontroller because it uses 100 I/O lines to run some gigantic 3D display, or because it uses fantastic I/O bandwidth, or because it's easily parallelized or appropriately parallelized on the FPGA, or let's say uses the FPGA to pre-process some information for the HPS. What comes to mind in this is word recognition, where you have a microphone hooked to the FPGA side, which is going to extract the MEL spectrum versus time, and then pass off the MEL spectrum versus time to the HPS, so that the front end of which is the FPGA, acts like the cochlea of your ear, which does the frequency analysis and sends the frequency analysis to your brain. This is easily parallelizable and works at more than real-time rate. You could probably do more than that. You could probably take the spectrum and then reduce it somewhat further before sending it over to the HPS for recognition. So an ideal combination of things is where you have a big chunk of data running on one or the other sides. It compresses down to a low-dimensional set of data and then expands on the other side back into some large problem. In this case, you're taking high bandwidth audio data, 48 kilohertz data. You're munching it down to a few Mel spectra a second, let's say 50 a second. So you're dropping the dimensionality quite a bit. And then you're sending that information over the HPS, which is doing some big database lookup or least squares matching or neural network or something. Another possibility is an FPGA, for FPGA application, is a neural net. And if you Google FPGA neural net, you'll find that there's all kinds of approaches for fitting rather large neural nets into rather small FPGAs, like using binary weights instead of floating point weights, or using binary decision functions instead of sigmoidal decision functions, which are expensive. So in that case, you might put Mel spectrum plus some piece of neural net on the FPGA side to drop the dimensionality even further, so that the HPS has to look at a fairly small data set for doing template matching. Typically, things that are very regular and parallel do well on the FPGA. Things that are logically deep and require lots of decisions are better on the HPS side. Anything else on Lab 4?
So the description said that we need to show the limits of the region. We will display that on the VG. Is it okay if we display it on the hex?
On the hex display, how would you do that to the appropriate precision?
Yeah, sorry, the time. It says the time taken should be displayed on the VGA.
Time needs to be displayed. That could be on the hex display, as long as it's in decimal and not hexadecimal. Hexadecimal milliseconds, or decimal milliseconds rather, and not some weird database, hexadecimal fractions of a microsecond or some crazy thing. Yeah. Okay, the coordinates. So now you can turn this around and say, how hard is it to write a character generator for your custom VGA? I've done that. Code's up on the web. The big part of that work is defining the ROM for each character. But luckily I found a ROM at, I think it was at BYU or Boston University, I can't remember which. Let me see if I can find that. It's in some obscure place. It's down in the older section under Stack CPU. This is the Pancake stack machine, which by the way also run on this architecture. It's a full stack machine with a compiler written in MATLAB. Why MATLAB? It's what I know. But somewhat placed down at the bottom, yes, a ROM character generator for VGA was built based on data blah blah at BYU. So the BYU file is just a character ROM. I reformatted it for Altera memory image file format. And so you can download it at load time into a block. I forget whether it was 1 or 2 blocks. Oh, that's a... Oh, this is the... Let's see if that'll open as a text file, or whether it'll just croak on that. I think it just croaked on that. Anyways, you give the ROM an ASCII code in standard ASCII, 8-bit ASCII, and what comes back is the bitmap, which you can then draw onto the VGA controller. So you could do that directly using your VGA device without using the HPS at all. Now, an interesting question is, since the HPS character overlay is a separate module from the VGA, could you feed the character output from the QSys bus into your custom VGA adapter? I do not know. I haven't tried that. That'd be interesting to try. Because then you could use the HPS to just draw the characters as an overlay. This character generator is a little bit better than the one supplied by as a QSys module, because it allows you to choose the color of the character. So that's in the stack machine page in the older section of the links. The reason I was playing around with a stack CPU originally was that I didn't like the NIOS processor, which was the old MIPS-like processor that was part of the IP from Altera, because there was too much hidden. You couldn't see the Verilog because it's encrypted. So you can't figure out how it actually works. The tool chain is kind of difficult to set up and understand. And so I wanted to have my own CPU with my own tool chain so I could play with it. Well, that's why I did this. It's a little CPU. It's only 2 or 3 pages of Verilog. Executes out of one M10K block easily. And it runs at 80 or 100 megahertz. So, in fact, there's in this section down here, in the DE2 section, there's a bunch of small CPUs, including a tiny CPU, the MuP3, from a guy named Hablin, and I modified it to have 4 instructions: add, multiply, branch, and halt, so I could use it for DSP. But it's a perfectly general CPU, and it's only one and a half pages of Verilog. I wrote an assembler for it, in MATLAB, of course. It's a very easily modifiable assembler. So it's certainly possible, in fact, easy to write your own CPU if that's your turn of mind. If you like to think about parallel CPUs, you could put dozens of these things on the FPGA before you run out of memory or logic. Anything else on Lab 4?
I'm not sure if you mentioned this before, but if you make each solver its own bus master, basically, and then you instantiate a bunch of those, are you going to have issues?
Issues? You'll have issues. Can you be more specific?
Like if all of them, if 2 solvers finish on the same cycle and try to write, is there some type of arbitration there? Or
So the bus arbitrates. The bus will, if the bus is not ready, it won't return an ACK. And therefore your bus master must hang until the ACK comes back. So the QSys bus will arbitrate. Now, that's a huge advantage. How much do you pay for that? I don't know yet. This is the first semester we've tried this. What happens when you had to put 10 bus masters on there that are all flailing the bus? I don't know. Informally, I've tried just one bus master writing as fast as I could write to the VGA memory, which is now only in SD-RAM. So I modified the code so that SD-RAM is shared 3 ways. It's shared between the HPS, the VGA controller, and a bus master. So it's being hit continuously to update the VGA display. The question is, how often can you write to it and not destroy the VGA display? So what I did was to set up a write loop, a memory access loop, that was 4 cycles long. Load the address, wait for the ACK, do something else, I forget what it was. And it trashed the VGA controller. It used way too many cycles. So then you can ask, how many cycles do you have to add in before the system is stable? And the answer is 8 cycles. 7 cycles didn't work, 8 cycles did. That says that every 12 cycles, 4 states of the state machine plus 8 wait states, you could write 1 value. Now, let's say, according to, I'm willing to dispute this or talk about it, but there's 307,200 pixels on a VGA screen. Times 8 bits, it ends up being something like 2.4 megabit. There's enough onboard memory to do that. That uses about a little over half of the onboard memory. So let's say that so you should be able to do M10K blocks on full color. But Istvan, did you have a problem with that? Did you run out of memory or something when you were trying to do that? Do I remember that, or am I making that up?
Because it only used 11 or 12 colors. We have 4 bits.
So you coded this as 4 bits. So you were in fact using 1/4 of the onboard memory to do the update. But even if you'd gone to 8 bits per, you could have fit it in, I believe. So it is possible to do this. Now you have your own write port on the onboard SRAM. There should be no limit to how fast you could write it aside from the state machine. So the SRAM lives on QSYS. It has 2 ports. One port is hooked to the VGA controller. The other port is shared between your bus masters. And that might be a good intermediate way of using QSYS while maintaining a high write rate. Because now you have no contention between your bus masters and the VGA controller, which is the other big bus user. The HPS is just sitting there doing nothing at this point. That allows you to use the HPS character generator stuff to overlay onto the image that you're generating. But you know, I'm making this up as I'm going along. This is the first time I've done this lab, so we'll see what people come up with. Does that make sense? Do people understand what I'm saying here? SRAM has 2 slave ports. And you'd hook one to the VGA and the other one to your bus masters. Butt master. Wrong. Bus masters times N. And as near as I can tell from the structure of the bus, when you put a new master on, it effectively instantiates a new bus. So I don't think there should be any contention between these two. I'm not sure about that. If underneath all of this abstraction of slaves and masters and serial communication, there's actually a packet network, which there may be. Can't quite tell. Then there may be contention between them. So right now, you're down to 40 milliseconds then. And one frame time is 16 milliseconds. So you're almost at animation rate. You're at half animation. So you could do 15 frames a second, almost 15 frames a second. Yeah. Do better than 15 frames a second. What else on Lab 4?
Are you able to do wider writes to the VGA memory? So set up your solvers to actually compute 4 pixels at a time.
Oh, what an interesting idea. So could you, since after all the bus is a 32-bit bus, could you do 4 bytes at a time? And I think so. I think what you need to do is when you set up the bus master, there's an address range and a width that's associated with it. And I think if you set up the width to 32 bits, that it will do the obvious thing. First of all, you have to have now word-aligned writes, but it will write the 4 bytes into memory on the same bus cycle. So that might be a way of speeding up by a factor of 4 at the expense of making the solver a little more complicated. Because now it's going to do 4 pixels before it calls for a write. And I believe this should work. And the reason I believe it should work was the first time I tried to interface a bus master to the VGA, for reasons that escape me, I set it up as a 16-bit bus. Although the VGA adapter was treating the memory as an 8-bit bus. And QSys just says, the fool doesn't know what he's doing, but I'll make it work. So it worked, except that it was only writing every other pixel. So what the hell is going on? So I was getting this weird screen door effect of one image transparent through the other because only every other pixel was being written. And it turns out it was because I was only writing the lower byte. And there was so I tried writing 2 bytes at a time, and it worked. But then I decided to go back to 8 bits because that was easier to think about. But yes, I believe that should work. Clumping up to 4 bytes should work. Interesting. There's lots of ways of doing this. So part of the way I've been fooling around with this is, as I said, to build a GPU that does rectangles, that being the simplest GPU I can think of. And right now, 10,000 pixels takes my GPU 2,400 cycles and takes the HPS 2,100 cycles. So it's a graphics decelerator. And it is because of bus contention. It's because the solver is 3 times faster than that, but the GPU is 3 times faster, but I can't write pixels fast enough. So after I get this documented up as working, now I'm going to try and use the M10K block, internal M10K blocks, to dual port the display memory. And if that doesn't speed it up because of some underlying bus contention, there's another thing to do, and that's to export the control signals from the SRAM bus on QSys out to the FPGA fabric and write it directly without going through QSys. That's kind of majorly homely, but it is fast. I'll try and have that documented up by tomorrow, kind of do all that. Won't help for Lab 4, but could help for final project. Any question on the final project at this point? Yes?
Are there any other interface with the camera without using NTSC? I don't know.
So the built-in video codec on the board is designed for NTSC or PAL. There is also a 5 megapixel camera that is available from Thoracic that plugs directly into the expansion port. I don't have any of those. One year that we asked for them, they sent them to us. Sent us 5. I think I still have 1 or 2 of those, but they're really old now. It's like version 1 and they're now at version 10. So if you go to the Thoracic site and look for daughter boards for this board, and you find something you like, send me an email and I will see if they'll give us 1 or 2 or 3. Otherwise, you should be able to interface any serial camera through the I/O ports. So a digital camera which you could barely read on a PIC32 is trivial to read on the FPGA. Yes?
What are these interfaces? So you're looking into one that's called CSI, and the problem with that is they all require some kind of physical hardware. Like CSI requires LVDS to make on the board. So is there something that would interface with 3.2 logic numbers?
Look at Adafruit.com. Sure. There are cameras which are serial read back. They give you a sync, a series of sync pulses, and they give you pixel information back in RGB serially. It's just a straight up serial protocol. It's pretty fast. Again, on FPGA, who cares? You got bandwidth. I think it's a 30 megahertz data stream. You can still do it.
If you configure the pins properly, you can also do LVDS directly from the FPGA.
That is correct. You can do that. You can do LVDS directly from the FPGA. Oh, you've got to go in and modify the properties of the I/O pin. I don't remember how to do that, but we can look it up. But that is possible. Do you remember how to do that?
Yeah.
Is it in the assignment editor?
Yeah.
So you open up the assignment editor and there's a pin layout there, and there's a whole bunch of properties that you can mess with per pin. There's somebody I think was using LVDS inputs to simulate an analog to digital comparator and do A to D conversions directly on the FPGA. That'd be entertaining because you get fantastic bandwidth that way. There is an A to D converter on this board. It's good to about 1 megahertz. An interesting final project would be a 16 input oscilloscope, logic analyzer. You plug the logic probes in, you clip them onto the PIC32 or whatever it is, you watch the waveforms, decode them into binary, decode them into ASCII, do all those kind of good things that logic analyzers do. You could also run those through the I/O pins. You could run logic analyzer through the I/O pins and get much better bandwidth that way. You do a mixed oscilloscope. So you use the digital I/O pins for 16 digital inputs, use the A to D converter for 2 or 4 analog waveforms. That'd be cool. Oh, and also throw in a synthesizer there so you could make a signal generator. Then you have your lab on an FPGA with data logging to the HPS.
Use the SD card as a slave on the bus.
Say again, SD card is a...
Can you make the SD card a slave on the bus, like directly write to it from the FPGA?
I believe you can. I think there's an SD card driver in the university program.
But would it do the slot on there, or would you have to like solder on?
It's got a slot. Oh, because you're saying that SD card is on the HPS side. I believe that there is a software switch you can throw to flip the SD card onto the FPGA side. Now, I don't know what Linux does when you do that. It probably does something unnice. However, you can boot these things bare metal. You can. There's instructions on in the getting started guide for booting the ARM bare metal, so that you can just run C programs on it with no stinking Linux. There's a couple of problems with that. No Ethernet, no USB, and the clock rate is 50 megahertz, not 900 megahertz. That's the big problem. To get around that, you have to set up the phase lock loops. I have yet to figure out how to do that bare metal. It's really complicated. In fact, I think the only way you're going to learn how to do that is to look at the boot code in the Linux kernel. That's a nasty project. What else? So, Wednesday, I suspect we should stay in the lab and work. Okay, is that all right, everybody? Friday will be 2-minute presentations of what you think what you're going to do for your final project. After that, what do you want to hear about? I've done a fair amount of DSP on these things. I've written 8 different variants of IIR filters. I've written a couple of pretty good CIC filters, cascaded integrator combs. Ever heard of those? Did you do those in some DSP class? They're designed for to be low-pass filters that are integrated into multi-rate sample systems, multi-sample rate systems. I've written at least one AM transmitter, one FM transmitter. AM transmitter broadcasts on the AM band at 1 megahertz. That's easy. You can do that by direct digital synthesis on the FPGA. It is illegal to broadcast on the... So you got to be a little careful. The FM transmitter, you can't get 100 megahertz direct digital synthesis out of these machines. So what I did was to synthesize 4 megahertz and to use the 15th harmonic. It's a square wave, so it has a strong 15th harmonic. It's 1/15 the strength of the fundamental. Use it and modulate the frequency by 0.1%, and you can play the result through a standard FM radio.
There's also a thing you can do where you put a PLL on the pin and then modulate the PLL.
That would work too if you had good control over the PLL. These tend to be integer PLLs, but so you can't quite do it with enough accuracy. But yes, that is also illegal because now you're broadcasting at 20 different frequencies, 4 megahertz apart. The first one happens to be in the middle of the marine distress band. So that's a bad thing. don't do that. Figure out another way of broadcasting if you're going to do that. So, yeah, there's a new DSP page, which is a little sparse because I haven't had time to do much. There's an audio loopback, which shows how to set up the audio and then loop it back to the audio input. A basic audio filtering, which shows how to set up 2.16 Butterworth IIR filters. And then a decimator that takes the 48 kilohertz down to 8 kilohertz, which is appropriate for speech work, for speech analysis. So it's a 6-to-1 decimator. And that's all I've had time to do. But the old page has more DSP on it, including 18-bit fixed point, 27-bit fixed point finite state machines, 18-bit fixed point using a CPU, using a parallel pipeline if you need to go 50 megahertz. If you're going to do filtering at television rate, this will filter at pixel rate. Probably the most useful one, though, is the floating point second order sections. Those are very stable filters. They're generalizable up to 6th or 8th order. They use very little space. They're quite fast. But I also do, soft radio transmitters, string synthesis. You want to simulate a string band? You can probably do 200 or 300 simulated strings on the FPGA in real time. And I messed around a little bit with adaptive noise cancellation. Narrow band. This was aimed at 60 hertz noise cancellation, so it uses a least mean squares filter. It's an adaptive filter designed to pull out 60 hertz and the low harmonics of 60 hertz. It's the second and third harmonic. So 120 and 180 hertz. Worked quite well. It was fixed point, didn't have enough accuracy, it's a little unstable, has a tendency to oscillate, needs work. But you get about 25 dBs of attenuation. So if you intend to do some DSP, come talk to me before you reinvent it. Done a bunch of it. There's some more. There's some IP for FIR filters and IIR filters available in the QSYS. I'm sorry, the IP library, not the QSYS library, the IP library. And clearly, you should use that if you want a FIR filter, particularly. What would you like to hear about?
What's the most bandwidth anyone's got between the HPS and the FPGA?
The most bandwidth the student got last year was 720,000 transactions per second, which is pathetic. But that's because we were still trying to figure out the lightweight versus the heavyweight bus. On the heavyweight bus, drawing to the VGA, you can get just under 6 million transactions per second. At one transfer, one memory write. So it'd be like a 32-bit write, or a 32-bit read. About 6 million a second. What I have not tried is the so-called streaming interface, which may well be faster. Some of the documentation refers to gigabit rates. I haven't figured out how to do that yet. I think it's possible. In particular, there's this terrifying concept of a portal between the FPGA and HPS memory that bypasses the cache. So you're guaranteed not to have cache coherency if you use that. And you have to be really careful, but I'll bet it's really high bandwidth. But I'm also band limited by how fast I can do experiments on this system. And I can read, just like you, I can read as much as I want, but I don't understand it until I've programmed it. So I'm plodding along, trying out each different thing. But truthfully, it'll be 3 years before I've gotten anywhere near through all the features of the FPGA. It's really complicated. What else? I played around a little bit with neural models on the FPGA. My interest was in spiking neural nets as opposed to convolutional neural nets or graded neural nets. So these tend to be time-based systems rather than amplitude-based systems. The amplitudes don't matter, they're fixed spikes just like in your nervous system. What matters is the timing of the events. And so I tried to come up with the simplest system I could that gives reasonable shaped events and allows for learning. I could talk much more about that. DSP, simple floating point hardware, we've already talked about. Digital differential analyzer we did in Lab 2, which next year will be Lab 1. Lab 1 this year will be gone. Lab 2 will be pushed into Lab 1. And then Labs 3 and 4 will each one of them will be probably either 2 or 3 weeks. VGA examples has the VGA control module that Skylar Schneider wrote. And again, it's reasonably well documented, and it should pretty much just work. I think it pretty much works. In that case, you throw away the VGA controller yeah, these are all examples of homemade controllers. You throw away the VGA adapter on QSys. So I'm going to be in lab, well, let's see, 2300 is in lab this afternoon. I'll be in lab tomorrow afternoon, most of the afternoon, most of Wednesday. So stop by with your questions. If you want to try out your 1-paragraph pitch on me before Friday, feel free. Thanks.